Okay, we're back at it for another video. So we're gonna do some more work on our switch mode power supply, our AC/DC flyback converter. And I'm just gonna put on a bit music. Happy, inspirational. So, okay. Okay, so as you can see, we're gonna step right back into where we left off yesterday, or last video. What we're building is a quasi-resonance flyback converter. Yeah, it's basically this right here is where we left off. We have a couple of components that are still undecided, and then we have some selected. So we have the QR flyback controller from Infineon. We have a MOSFET to handle the input voltage and the maximum drain to source current here. We have selected a transformer and a bridge rectifier. So I can open the MOSFET. We selected, which is this one. It had a drain to source voltage of 900. So it will handle this the peak voltage of 375 on the input, plus reflected voltage, and also voltage spikes due to the leakage inductance when the MOSFET is switched off. So when the MOSFET is off, VDS is here, and we need to account for, roughly 875 volts, assuming 400 spike voltage. I'm not sure, that's probably way over dimensioned or something, but I found this MOSFET for quite okay price. 22 crowns, I guess. It's an important component, so we will just leave it for now. We can always go back later on and redo our design and do it more cost efficiently, which is the fun part too. Understanding how the circuit works and how it's built and why we choose the components we do. Yes, and we chose this MOSFET so it would handle worst case voltages. Then we have also the drain to source current, which was our drain current, continuous drain current, which is 5.4 ampere. And this should be, according to my research, twice the primary or the peak current. The primary peak current. I've also seen just another margin formula, just 1.5 times the output current. So I guess that also works. I'm not sure. But anyways, that is what we have set. So this will work. We will later on go into simulating these circuits and to get a better picture as well. to learn how that is done. So now if you've been watching previous episodes of this series, we've been following this guide from techwebrom.com for an AC/DC design. It's an isolated flyback converter circuit, just like we're building. Although here it's a simpler controller, it's not a quasi-resonant, it's a fixed frequency one. So we already selected the MOSFET, and the next step would be to select the input capacitor and the snubber circuit. And in this case, we have an RCD clamp circuit, which would work as following. So we know that we have some inductance here. So we would and the peak current, I guess you would use the peak current, so you would be able to calculate the energy from this magnetic field. So as current is flowing through the coil, it generates a magnetic field, and we can calculate what the energy is, how much energy it introduces, which when the MOSFET is switched off results in a very high voltage spike that we need to account for. I'm not sure if you need to do it or if it's just very good practice to do it, but anyways, it works as following. So the diode is there to direct the current this way, and then the capacitor would be sized to properly manage the energy stored by the inductor. So when the switch is off, the inductor or the inductance, the magnetic field of the primary side coil will collapse, resulting in a voltage spike. That energy will travel this way, and the capacitor has to compensate for that and absorb all that energy. So it really has a one-to-one, almost a one-to-one responsibility in a way. And we also sized a resistor to just limit the current, I guess. I remember reading about it exactly, but it has to be that. What else would it be? Protect switching transistors from surges that occur at the input. So here's an RCD clamp as well. So this is what they have done. I just want to jump ahead and confirm what I just said. The gap is provided in a transformer core so that leakage magnetic flux is increased and a leakage inductance occurs. Yeah, that is where the energy is located on. Switching current flows in the leakage inductance as well, and energy is accumulated, but it's not coupled with the other windings, and so power is not transferred, and a surge voltage occurs across the MOSFET drain and source. When the surge voltage that occurs exceeds the MOSFET voltage rating, there's a possibility of MOSFET failure. Yeah, and then it's we can calculate which values they should be. Okay. Okay, but then the input capacitor, so in their case 450 volts and 100 microfarad capacitance, and yeah, 450 voltage rating. The first purpose has two principal purposes, but it's essentially connected in anticipation of situations in which input voltage momentarily drops or is cut off. The first purpose is for when the AC input is momentarily shut off, the input voltage is completely gone, but power can be supplied, albeit for a short period due to the charge stored in the capacitor. The second purpose has to do with the fact that the MOSFET used as the switching transistor turns large current on and off extremely rapidly when the input response cannot keep up with the switching. Where the input impedance is high, the input voltage drops for a short time, and this is augmented by C1. In any case, when the input voltage falls below the required voltage, an anomaly of course occurs in the output voltage and problems arise in the operation. It's according to the criteria indicated in the table below. Power out is determined from the specification of this design, calculated based on the table. We have P out. So we have P out is 24 watt. And 2 times the coefficients in this table are for full wave rectification. The capacitance must be adjusted according to differences in conditions and the specifications for input hold time during momentary shutoffs. So it should be set to the peak voltage 400 volts or higher, hence the capacitor C1 is selected to be 100 microfarad and 450. Electrolytic capacitors are nearly always used. Okay. Why is it 2 times? Okay. So C in I could definitely make like a design guide template, or maybe yeah, something in the future. C in and just do like this. So we need to know V in max, which is V in, no, VAC max times square root of 2. And this is 265 volt AC times 1.41, which is roughly 375 volts. I think it should be. So it has to at least be C in should be greater, or voltage rating greater than 375 volts. Capacitance power, or P out times 2. I don't know why. Why? The capacitor needs to be large enough to maintain a minimum acceptable voltage level at the input of the power converter, minimizing voltage drop during low input voltage. Selecting input capacitor. So the first objective is to reduce ripple voltage amplitude seen at the input of the module. This reduces the RMS ripple current to a level which can be handled by bulk capacitors. Large bulk capacitors do not reduce ripple voltage. And this is more in DC, I guess. So the role of the input capacitor is to reduce voltage fluctuations from the rectifier to a level acceptable. So voltage fluctuations here to a level acceptable by the subsequent DC-DC converter load, handle RMS ripple currents, and it needs to tolerate the RMS rip current it will experience, which is influenced by the input voltage ripple and the duty cycle of the switching converter. Okay. So ceramic capacitors, they're more or they're better at reducing the ripple voltage. While the bulk capacitors, such as aluminum electrolytic or tantalum capacitors, provide large capacitance needed for energy storage, but their higher ESR makes them less effective at ripple reduction on their own. Here's also some good we can have a look at. There are other requirements for the input capacitor. Must be rated for AC mains voltage, capacitance variation due to operating voltage and temperature. Okay, let's not, I'm not sure why it is this way, but 2 times 24 watt is 48. So 48. So 47. Yeah, so for now, just let's use this 24 watts times 2 equals 48. So we select a 47 microfarad capacitor then. rectifier. Rectifiers, yes. Package, I don't know. Now what am I doing? I need a capacitor. And then the information we have is that it needs to be 47 microfarad. And then the voltage rating had to be at least above 375. So 450. Let's do 450 or a few more. 450. Let's see what we get. So we have aluminum electrolytic capacitors. Yeah, it's mostly that. And we can select low ESR to maybe have a better voltage ripple, because that's the point also, not just energy storage. High frequency. Maybe try that. Then we get 1. Okay. Maybe we take it away. And then we have a look. Look at the ones in stock, active. So we have 66 capacitors to choose from. We look at price too. Go for the cheapest. Oh, I mean the first one has a lot in stock. Radial leaded, 450 volts DC. Rated voltage range. Question is if it's high enough margin. They chose 450. I'm curious which one they chose. Yeah. Okay, but let's select this one. And we'll all review it more anyways. Ripple current 500 milliampere. It's important to compensate for input currents that are drawn in due to momentary input power shutoffs and switching. Selecting input capacitor and AC/DC design. There's a bunch of videos on this. Rated voltage, rated ripple current, and ripple heat generation characteristics. The following should be borne in mind as premises for selection. Now, it's actually a DC-DC design. Then use a rule of thumb like 1 to 2 microfarad per watt. So per watt to... okay. So it's a rule of thumb. So 1 to 2 microfarads per watt. And input first determine the maximum input power, then use a rule of thumb. Yeah. So we want to select this one. The bus capacitor, sometimes referred to as the bulk capacitor, stores and delivers energy W to the power system. It's charged every half line cycle by low frequency current and discharged continuously by the high frequency current pulses drawn by the converter. So selecting a bus capacitor voltage rating greater than the maximum bus voltage, check. Yes, 265 times the square root of 2, 375 volts. Assuming a minimum DC bus voltage of 75 volts, calculate the average input current of the converter. And select an initial bus capacitor value based on 120 microfarads per amps. So that at least gives a bit of a bigger C-bus in it. Times the out divided by, was it V bus min, so V in min times N, which is the efficiency. So like this, like this. Times 48, no, 24, yes, what, divided by here I've written 95, wait. So minimum was 85 times 1.41, which is 120. Okay, let's just use 75, it's fine. 75 times 80, or 0.85 then. Since we wanted 85 efficiency, 85%. Okay. So this is 120 divided by 1 times 24 divided by parentheses 75 times 0.85. $45.1. So let's still select then 47 microfarads. So what this mean? We select this. Why do we select it? And the model presented in figure 2. Oh, okay, so here we can simulate it. We'll save this. Cool, but then this still applies, so we will use that. But at least now we understand the calculations a little bit more. Selection. So. So we selected another component, and then we're on the RCD clamp circuit. I wish I could just understand a little bit. It stores and delivers energy, W, to the power system. Yeah, so we can calculate the energy storage using the capacitance and the voltage squared. Capacitor C-bus is charged every half-life cycle. This action results in a low frequency AC current. And a high frequency AC current passing through C-bus. Okay, anyways. Anyways, we have selected a component, so. I'll be right back. Okay, I'm back. I am back. Back again. Yeah, but I will end the video for today. My legs are killing me, and I need to lay down. But anyways, we selected this input capacitor that are capable of handling the voltage, the maximum DC voltage, 375. We choose a voltage rating on the capacitor to exceed that by some margin. I chose 450 volts, also a little bit influenced by this design guide that also do that. But we will revisit every selection eventually. But it will be nice to see this all selected, so we can maybe even do some simulations of the entire circuit. Not entire circuit, but you know, following a little bit examples along the way, such as this one. But yeah, thank you for joining me. I will continue in the next one. Bye bye.